June 17, 2026, 6:56 p.m., Coordinated Universal Time, somewhere in the central Atlantic Ocean, at a depth of roughly 10 kilometers beneath the seafloor, rock that had been under stress for years finally moved. The earthquake that resulted was magnitude 6. It was recorded by 168 seismic monitoring stations operated by the United States Geological Survey, spread across the planet, each one detecting the vibrations spreading outward from the event at thousands of kilometers per hour through the solid earth. No tsunami was triggered, no coastal community was affected, no building shook. On the surface of the Atlantic Ocean above the event, a ship might have noticed nothing unusual at all. The earthquake happened where earthquakes of this kind almost always happen. On the mid-Atlantic ridge, the underwater mountain chain running the length of the Atlantic, where the South American and African plates are slowly being pulled apart. The epicenter was located at approximately 0.5 degrees south latitude, 20 degrees west longitude, the central mid-Atlantic ridge, in the open South Atlantic, more than 1,000 kilometers from the nearest populated land. This event was not unusual for the mid-Atlantic ridge. Earthquakes of magnitude 6 and above occur on the ridge regularly. Seismic swarms, clusters of hundreds of smaller earthquakes occurring over days and weeks, are documented throughout the ridge's history. They are among the most ordinary things the ridge does. But the reason these ordinary events are scientifically important, the reason they are being systematically studied in a paper published in Frontiers in Earth Science in February 2026, the reason, a 2021 Nature paper by researchers from the University of Southampton, changed how geologists think about what drives mid-ocean ridges, and the reason, the 2022 seismic sequence at 54 degrees north revealed the migration of magma through the oceanic crust in real time, is that each of these events is not just an earthquake. It is a moment in the process by which the Atlantic Ocean is growing, right now, tonight, millimeter by millimeter. The ocean floor beneath the Atlantic is cracking open, and new rock is being pushed into the gap. This has been happening for 180 million years, and geologists have now, for the first time in detail, begun watching individual episodes of it unfold in real time. The Atlantic Ocean did not always exist. 200 million years ago, where the Atlantic is today, there was a supercontinent, Pangaea. The landmass that would become North America was pressed against the landmass that would become Africa and Europe. They were one thing. They are now separated by more than 6,000 kilometers of ocean. That separation happened one crack at a time, one dike intrusion at a time, one seismic swarm at a time. The process that made the Atlantic Ocean is the same process that a magnitude 6 earthquake on the mid-Atlantic ridge in June 2026 represents. The ERTH's crust parting, magma filling the gap, new rock forming, and the two plates moving fractionally further apart. The crack that is growing in the Atlantic Ocean floor is not a new crack. It is the oldest ongoing geological process in the basin. What is new is that we can now watch it happen. The scale of what has been accomplished since the rift began is worth dwelling on. 200 million years ago, the earliest Proto-Atlantic was a narrow seaway, perhaps comparable in width to the modern Red Sea. Africa and North America were close enough that an animal on one continent could, in principle, have seen the other across the water. The ocean between them now is wider than the United States, is from coast to coast. Every centimeter of that distance accumulated through the same process, the same dike intrusions, the same seismic swarms, the same rift valley filling with new magma, that is producing a M6 earthquake on the ridge today. The current event is not distinguished from any of the millions of similar events that preceded it. It is simple. Why the current one, the latest in an unbroken sequence that has been running since before the age of dinosaurs. This video is about the Mid-Atlantic Ridge, how it works, and what the most recent science has revealed about the processes driving it. It is about the September 2022 seismic sequence at 54 degrees north, where more than 60 earthquakes occurred over several days. Their locations migrating southward in a pattern that scientists interpreted as magma pushing its way laterally through the oceanic crust beneath the Rift Valley. It is about the 2021 University of Southampton study, published in Nature, which placed 39 seismometers directly on the seafloor along the equatorial mid-Atlantic ridge and found something that had been assumed for decades to be wrong. That the ridge is not a passive feature but an active one, driven from below by upwelling from the deep mantle, in ways that geologists are still working to understand. It is about the systematic study of 24 years of earthquake swarm data on the northern mid-Atlantic ridge, published in February 2026, in Frontiers in Earth Science. That is building the statistical foundation needed to distinguish the seismic signatures of magmatic intrusion from pure tectonic faulting. In a region where both processes produce earthquakes, and where the ocean obscures direct observation of almost everything happening on the seafloor. And it is about what remains genuinely unknown. Whether any particular seismic swarm on the mid-Atlantic ridge precedes a volcanic eruption, how much of the ridge's spreading happens in large discrete events, versus slow continuous creep, and what the active upwelling discovered beneath the equatorial ridge means for how the ridge system as a whole is driven. By the end of this video, you will understand how seafloor spreading actually works at the level of individual geological events, what a blind dike intrusion is, and how its signature appears in seismic data, what the Southampton study changed about the model of mid-ocean ridges, and why the mid-Atlantic ridge produces earthquakes continuously while remaining almost entirely invisible to most of the people on the planet. It is slowly reshaping. How does the Atlantic Ocean floor actually grow? At the level of individual geological events, rather than the abstract summary that continents drift apart. What is a blind dike? And how does magma push through solid rock in a way that produces an earthquake swarm that migrates through space over days? What did placing 39 seismometers directly on the seafloor of the mid-Atlantic ridge reveal that decades of monitoring from land stations had missed? Why is it so difficult to monitor the mid-Atlantic ridge compared to land-based geological systems, and how does that monitoring gap affect our understanding of what is happening there? And can seismic monitoring tell us whether a swarm on the mid-Atlantic ridge is going to produce a volcanic eruption? Or is that prediction still beyond current capability? This is not a video about an imminent geological catastrophe. The mid-Atlantic ridge does not produce tsunamis from its earthquakes, because earthquakes at slow-spreading mid-ocean ridges do not generate the kind of rapid seafloor displacement that causes tsunamis. The ridge does not threaten coastal populations. Its activity is not unusual by geological standards. This is also not a video that treats seafloor spreading as a textbook process, too well understood to be interesting. The Southampton Nature paper from 2021 specifically challenged the long-held assumption that mid-ocean ridges are passive features pulled apart by forces acting elsewhere. The 2022 seismic sequence at 54 degrees N gave scientists their clearest view yet of a magmatic intrusion event unfolding in real time beneath the North Atlantic. And the 2026 Frontiers paper is the first systematic large-scale analyses of 24 years of swarm data on the northern ridge. The honest version of this story is of a geological process that everyone learns about in school, that is genuinely ongoing right now, that is producing M6 earthquakes in June 2026, and that remains, in its detailed mechanics and in its driving forces, less well understood than most people who learned plate tectonics in a classroom realize. Before we go further, if the idea that the Earth's crust is cracking open beneath the Atlantic Ocean right now, in a process that has been running continuously for 180 million years and is still not fully understood, is the kind of thing that pulls you in, subscribe to Galaxy Pulse. We go into the details. Now, back to the mid-Atlantic ridge, and to the process by which an ocean grows. How the Atlantic grows, and where the mystery lies. Base explanation. The mid-Atlantic ridge is the longest mountain chain on Earth. It runs for roughly 16,000 kilometers from Jan Mayen Island, north of Iceland, to a point in the South Atlantic, then continues as related structures around the southern tip of Africa. Most of it lies between 2,000 and 3,000 meters below the ocean surface. Hidden beneath water that is essentially opaque to the direct observation that geologists use on land. The ridge is not a single continuous feature, but a series of segments, each a few hundred kilometers long, offset from the next by transform faults, horizontal fractures, along which the two ridge segments on either side of the offset are sliding past each other, rather than spreading apart. The ridge is the surface expression of a plate boundary where two tectonic plates are moving apart. In the northern Atlantic, the North American plate and the Eurasian plate are diverging. In the southern and central Atlantic, the South American plate and the African plate are diverging. The June 2026 M6 earthquake occurred on the central portion of the ridge, where the African and South American plates are separating. The rate at which they are diverging, the spreading rate of the mid-Atlantic ridge, is approximately 25 millimeters per year. This is considered slow by the standards of global mid-ocean ridges. The East Pacific Rise, the analogous feature in the Pacific Ocean, spreads at up to 150 millimeters per year. The mid-Atlantic ridge is a slow spreader, which means it has a distinctive physical character. Rather than the broad, smooth arch of a fast-spreading ridge, it has a rift valley down its center, a graben, a rift structure where the axial valley floor sits below the surrounding ridge flanks, bounded by faults on either side. This rift valley is where most of the geological action happens. It is where new oceanic crust is created. It is where the earthquakes cluster. It is where magma, rising from the mantle below, periodically intrudes into the crust. The basic process is understood in broad outline. Hot mantle material rises beneath the ridge axis. The mantle rock, under lower pressure near the surface of the Earth than it was at depth, undergoes decompression melting. It partially melts not because the temperature increases, but because the pressure decreases and the rock crosses the solidus, the boundary between solid and partially molten states. This melt, called basaltic magma, is less dense than the surrounding solid mantle, so it rises. It collects in a magma reservoir, if one exists, or rises more directly toward the surface. When it erupts, or intrudes at the ridge axis, it adds new material to the oceanic crust. As this new crust moves away from the ridge axis on both sides, carried by the divergence of the plates, the rift is filled again, and the process repeats. To put the slow spreading rate in physical terms, 25 millimeters per year is about the rate at which a human fingernail grows. It is imperceptibly slow by human standards. But applied continuously over 180 million years, this rate has opened an ocean that is now 6,000 kilometers wide. The geometry makes sense once you do the arithmetic. 25 mm/ times 180 million years equals 500 kilometers on each side of the ridge, for a total of 9,000 kilometers of Atlantic seafloor created, which accounts for most of the current width, with the difference explained by the non-constant spreading rate over geological time, and the addition of continental margin material from the initial rifting. The result is that the oceanic crust is youngest at the ridge axis, and gets progressively older moving away from the ridge in either direction. The oldest oceanic crust in the Atlantic, near the continental margins, is approximately 180 million years old. The youngest, at the ridge axis right now, is forming today. This is how the Atlantic Ocean grows. Not continuously and smoothly, like a balloon inflating, but episodically, in pulses driven by individual dike intrusions and eruptions, each of which adds a thin layer of new rock to the seafloor and pushes the two plates fractionally further apart. The actual spreading process is, in the language of geology, intermittent and non-uniform. Individual ridge segments may go decades or centuries without a significant magmatic event, then experience a series of dike intrusion ions in rapid succession. The 25 mm/ figure is an average over very long timescales and entire ridge lengths, not a constant rate at any given point. Normal versus strange contrast under the model that dominated geological thinking for most of the 20th century. Mid-ocean ridges are largely passive features. In this model, the plates move apart because of forces acting at their far edges, subduction zones, where dense oceanic crust sinks into the mantle under its own weight, pulling the rest of the plate behind it. This process, called slab pull, was considered the primary driver of plate motion. The ridge simply fills in the gap created by the plates pulling apart, like the gap in a piece of stretched taffy. The magma rises not because it is being pushed from below, but because a hole opens up for it. This model is not wrong, exactly. Slab pull is a real force. Subduction zones do pull the plates, but it implies that the ridge is a passive consequence of forces acting elsewhere, a wound that fills in rather than an active geological system with its own driving dynamics. The 2021 Nature paper by Agius, Richard, Harmon, Thorheimne, and Kendall, with co-authorship from University of Southampton and other institutions, complicated this picture significantly. The team had deployed 39 ocean bottom seismometers and 39 ocean bottom magnetotelluric instruments directly on the seafloor of the equatorial mid-Atlantic ridge, the PILAB experiment, for passive imaging of the lithosphere-asthenosphere boundary, in a region between about 1 and 4 degrees north latitude near the chain fracture zone. The instruments recorded the seismic waves produced by distant earthquakes, and used them to image the structure of the mantle beneath the ridge. The same general principle as a medical ultrasound, but using earthquake waves instead of sound waves. What they found was unexpected. Beneath the equatorial mid-Atlantic ridge, the mantle transition zone, the layer of rock sitting between 410 and 660 kilometers depth, where the mineral composition changes due to pressure, was significantly thinner than El-Suhur. Specifically, the 1660 km discontinuity was uplifted by about 10 kilometers over a broad region roughly 600 kilometers wide, while the 410 km discontinuity was slightly depressed. A thin mantle transition zone is a sign of elevated temperatures in the mantle in that region, and elevated temperatures drive upwelling, the rise of hot material toward T surface. To understand why the depth of these discontinuities matters, it helps to think about what causes them. The mantle transition zone is defined by two seismic discontinuities, abrupt changes in seismic wave velocity that correspond to phase transitions in heat-dominant mantle minerals. At about 410 km depth, olivine, the most abundant upper mantle mineral, transforms to a denser form called wadsleyite. At about 1660 km depth, the mineral structure changes again to an even denser phase that does not persist in the upper mantle. Both of these transitions are temperature sensitive. In hotter mantle, the 410 km transition occurs at slightly greater depth. The discontinuity is depressed, and the 1660 km transition occurs at slightly shallower depth. The discontinuate Y is uplifted. A thin transition zone, one where the 1660 km discontinuity is shallower than average and the 410 km discontinuity is deeper, therefore indicates anomalously hot mantle in that depth range. Hot mantle at depth is buoyant, and buoyant hot mantle rises. The thin transition zone beneath the equatorial ridge, therefore, implies a column of unusually hot mantle beneath that ridge segment, rising toward the surface, not merely filling the space created by the parting plates, but actively ascending. In other words, something was being pushed from below, not just pulled apart from the sides. The paper, published in Nature Volume 589, January 2021, concluded that material transfer from the lower to the upper mantle at this location, either continuous or episodic, might be actively contributing to seafloor spreading, challenging the purely passive ridge model, as lead author Matthew Agius described it. It was assumed that these gravitational forces, which are pulling down, are contributing to the spreads at the ridges. The new data suggested the picture was more complex. This does not eliminate slab pull as a factor, but it suggests that beneath at least parts of the mid-Atlantic ridge, the ridge is a more active participant in the dynamics of plate motion than the conventional model assumed, not merely a passive fissure being widened from outside, but a system with upwelling mantle dynamics of its own. The 2022 seismic sequence at 54 degrees and the September 2022 seismic sequence at 54 degrees north on the mid-Atlantic ridge, documented in a study published in Geophysical Research Letters by Seska and colleagues at the GFZ German Research Center for Geosciences in 2023, is one of the most detailed observations ever made of a mid-ocean ridge spreading event in progress. It began on September 26, 2022, with a magnitude 4.8 earthquake in the axial valley of the mid-Atlantic ridge at approximately 54 degrees north, about 125 kilometers north of the Charlie Gibbs fracture zone. What followed was an unusual extended sequence. Over the following weeks, more than 60 earthquakes with well-constrained focal mechanisms were identified and analyzed, with seismicity continuing through December 2022. The researchers derived 77 moment tensor solutions from the sequence. But the striking feature was not just the number of events, it was where they occurred. The earthquake locations were migrating. Each successive event was occurring slightly further south than the last. The normal faulting extensional earthquakes propagated from a northern initiation point at approximately 54.1 degrees N southward, reaching their final extent between approximately 53.5 degrees and 53.7 degrees N, a total along axis distance of roughly 60 kilometers. The migration rate implied by this pattern was approximately 0.6 kilometers per hour during the active propagation phase. To understand why this is so diagnostically meaningful, it helps to think about what earthquake migration means physically. In a purely tectonic stress environment, Earthquakes release stress stored in rocks along existing faults. These events cluster in space and time, but do not necessarily migrate systematically in one direction. Random fault slip produces spatially clustered but directionally incoherent seismicity. A systematic southward migration at a measurable rate is the signature of a single physica L process propagating through the crust, and the most natural physical process that propagates through the crust at this rate is the advance of a magma-filled crack. The interpretation reached by Seska and colleagues was that they were witnessing a blind dike intrusion. Magma pushing its way laterally through the oceanic crust beneath the Rift Valley, propagating southward through the rock. The earthquakes were being generated not by purely tectonic stresses, but by the crack tip of the advancing magma intrusion, the leading edge of the dike forcing its way through solid rock. But then, something even more unusual happened. Roughly 80 hours into the earthquake swarm, a magnitude 5.7 earthquake occurred approximately 25 kilometers east of the axial extensional band. This earthquake had a thrust faulting mechanism, meaning it was compressional rather than extensional. In the axial valley of a mid-ocean ridge, where all the expected stresses are extensional and the expected earthquakes are normal faulting events, a thrust earthquake is anomalous. Between late September 2022 and January 2023, 11 more thrust events occurred on north-south striking planes, both east and west of the axis, forming two narrow bands approximately 25 kilometers on either side of the rift zone. The explanation that the research team developed is mechanically elegant. The dike intruding into the axial crust added volume to the crust locally. As it inflated the crust from inside, it pushed the ridge flanks outward. The ridge flanks, already under H horizontal stress from the plate boundary dynamics, were pushed past a threshold, and the outer portions of the ridge experienced compressional failure. In a region of the ocean floor where compression is essentially never expected, the magmatic intrusion at the center created compressional stresses at the sides. The dike was squeezing the ridge from the inside out. This sequence was, the researchers noted, unusual enough that no previous well-studied seismic event at a mid-ocean ridge had generated a clearly linked off-axis compressional sequence of this character. It revealed a coupling between on-axis magmatic processes and off-axis crustal stress that had been theoretically possible, but never clearly observed in the mid-Atlantic ridge context. Three concepts that matter. Three concepts are essential for following what comes next. The first is what a dike is, and why its intrusion produces migrating earthquakes. A dike is a thin sheet of magma that has been injected into pre-existing rock, forcing the rock apart to make room for itself. In continental geology, dikes are common fetu res, often visible as vertical dark bands cutting through older rock. In oceanic geology at mid-ocean ridges, dikes form when magma from a reservoir or rising directly from the mantle is injected sideways into the brittle upper oceanic crust. The leading edge of the dike, the crack tip advancing through rock, produces earthquakes by breaking the rock ahead of it. Because the crack tip moves, the earthquakes it produces also move, creating the migration pattern that was the diagnostic signature of the 202.2 event. The migration rate of approximately 0.6 km/h in the 2022 case is characteristic of how quickly magma can advance through cold oceanic crust at these depths. The second is the distinction between a blind dike and a surface eruption. A blind dike intrudes into the crust without reaching the seafloor. It solidifies in place, adding a thin layer of new igneous rock to the interior of the crust without producing a lava flow visible on the seafloor surface. Most of the volume added to the oceanic crust at mid-ocean ridges is added this way, by the accumulation of solidified dike material, rather than by surface lava flows. In the 2022 event, the dike was interpreted as likely blind because no hydrothermal plume was detected above the event site. Hydrothermal plumes being a characteristic signature of submarine volcanic eruptions. The absence of a detected plume does not conclusively prove no eruption occurred. Small L eruptions at slow-spreading ridges may not produce detectable plumes, but it is the expected observation if the intrusion remained below the seafloor. The third is the monitoring challenge. The Mid-Atlantic Ridge is, as the 2026 Frontiers Earth Science paper notes explicitly, positioned at great distances from on-land seismic stations. The seismometers that form global seismic networks are primarily located on land, where they are easiest to install and maintain. Detecting and accurately locating earthquakes on the Mid-Atlantic Ridge using these land-based networks is inherently less precise than detecting earthquakes near dense land-based networks. The 2022 event was detected and studied primarily through analysis of regional and teleseismic data, recordings from stations across the Atlantic Basin and worldwide, rather than from local instruments near the event. To get the kind of detailed picture that local seismometers would provide requires deploying ocean bottom seismometers directly on the seafloor, which is expensive, technical lie demanding, and covers only small areas for limited time periods. Stakes rise here is why the monitoring challenge matters beyond just scientific accuracy. The Mid-Atlantic Ridge produces seismic swarms continuously. The 2026 Frontiers paper by Zhang, Rich, and Heron at the University of Toronto analyzed earthquake data from 2000 through September 2024 on the northern portion of the ridge between 52 and 63 degrees north, a stretch that includes the Reykjanes Ridge extending south from Iceland. This stretch alone regularly produces clusters of earthquakes that, using land-based monitoring, can be identified as swarms but cannot easily be distinguished as magmatic or tectonic in origin. This distinction matters enormously for understanding what the ridge is doing. A magmatic swarm, driven by a dike intrusion or a volcanic eruption, is a spreading event. New crust is being created, the plates are being pushed further apart, magma is entering the system. A tectonic swarm, driven by purely mechanical stress release on existing faults, is a stress adjustment. The plates are moving relative to each other without significant new magma input. The two processes produce different seismic signatures, but those signatures overlap sufficiently that distinguishing them from distant stations is often ambiguous. The June 17, 2026 magnitude 6 earthquake on the central Mid-Atlantic Ridge is a single large event in this ongoing background. At magnitude 6, it is large enough to be clearly detected and located. But whether it was a purely tectonic event on a pre-existing fault, or whether it was associated with a dike intrusion or other magmatic activity, cannot be determined from the earthquake size or location alone. It requires the kind of sequence analysis, including looking for smaller foreshocks and aftershock (KS), examining the focal mechanism in detail, and checking for any evidence of seismic migration, that the 2022 study carried out so effectively for the sequence at 54 degrees N. Mini cliffhanger, the 2022 sequence at 54 degrees N. The 2021 Southampton Nature paper, the 2026 Systematic Swarm Analysis, and the June 2026 M6 earthquake are all pieces of the same larger picture. A geological system that is active, monitored, partially understood, and full of open questions. Among those open questions, one stands out as both the most practically significant and the most scientifically interesting. Can seismic monitoring predict when a mid-Atlantic ridge swarm is going to produce a volcanic eruption? The answer, as of mid-2026, is sometimes, partially, and not reliably enough to be called prediction. The reason is connected to the fundamental monitoring challenge and to a deeper physical question about how magma moves in the oceanic crust. The monitoring, the models, and the open questions. The monitoring of the mid-Atlantic ridge involves three main classes of instrument, each with different strengths and different limitations. The first is the global land-based seismic network, hundreds of seismometers on every continent, and many oceanic islands record ground motion continuously and transmit data to central analysis centers in near real time. These networks detect every significant earthquake on the mid-Atlantic ridge, typically locating events of magnitude 4 and above with reasonable accuracy. The 2026 Frontiers Earth Science paper by Zhang, Rich, and Heron used data from the USGS Global Catalog spanning 2000 to September 2024 to analyze earthquake swarms between 52 and 63 degrees north on the mid-Atlantic ridge. They applied cluster analysis algorithms to identify swarm events within the catalog, characterize their spatial and temporal patterns, and assess whether the existing catalog data is sufficient to classify swarms as magmatic or tectonic without additional local instrumentation. Their co-inclusion. The global catalog is sufficient to identify swarms and their general characteristics, but the location, uncertainties, and detection thresholds of land-based monitoring limit the detailed interpretation possible without local ocean bottom seismometers. The second class of instrument is hydrophone arrays. The ocean transmits sound efficiently, and earthquakes and eruptions generate acoustic waves called T-waves that travel through the ocean's seafloor channel, a zone of minimum sound velocity in the water column that acts as a natural acoustic waveguide, trapping sound energy and allowing it to travel thousands of kilometers with minimal attenuation. A network of hydrophones, operated partially by NOAA and other agencies, can detect and locate ocean acoustic events, including submarine eruptions and small earthquakes invisible to land-based seismic networks. The Atlantic is less well covered by these systems than the Pacific, but some monitoring capability exists. The third class, and the most informative but least extensive, is ocean bottom seismometers. These are self-contained seismometer packages that can be deployed on the seafloor, anchor themselves, and record data for periods of months to years before releasing their weights and floating to the surface for data recovery. Deployed in arrays of tens to hundreds of instruments near specific ridge segments, they provide local, high-precision seismic data that land-based monitoring cannot achieve at these distances. The Southampton PILAB study used 39 ocean bottom seismometers deployed for approximately 1 year along the equatorial mid-Atlantic ridge. The data they collected was qualitatively different from what any land-based network could provide. Precise location for small earthquakes, detailed imaging of the mantle structure beneath the ridge, and the ability to detect events too small to register on distant instruments. But the deployment covered only a small section of the ridge for a limited time, and the data recovery required physically retrieving the instruments from the seafloor. This is the monitoring picture. Good global coverage of large events, partial acoustic coverage of intermediate events, and sporadic local coverage of specific segments through temporary ocean bottom deployments. The mid-Atlantic ridge is roughly 16,000 kilometers long. The total seafloor instrumented at any given time by ocean bottom seismometers is a fraction of a percent of this length. One of the most practically significant questions in mid-ocean ridge science is whether volcanic eruptions at submarine ridges can be predicted. On land, the best studied volcanoes have well-characterized precursory seismic signals. Before an eruption at Kilauea, or at Mount St. Helens, or at Etna, seismicity increases in distinctive patterns as magma moves toward the surface. Ground deformation, measured by GPS and tiltmeters, reflects the inflation of magma reservoirs. Gas emissions change composition and intensity. Taken together, these signals allow geologists to issue eruption warnings days to weeks in advance for well-monitored systems. The Mid-Atlantic Ridge has none of this infrastructure for most of its length. There are no GPS sensors on the seafloor along the ridge axis. There are no tiltmeters. There are no gas sensors monitoring volcanic emissions in real time. The 2022 event at 54 degrees N illustrates both the progress that has been made and the limits of what current monitoring can tell us. The seismic sequence was detected in real time by global networks. The migration pattern was identified through retrospective analyses, working backward from the recorded earthquake locations to reconstruct the southward propagation of the dike tip. Researchers knew a significant seismic sequence was underway. They did not know in real time that it represented a dike intrusion migrating southward. That interpretation required careful analysis after the fact. Whether the dike reached the seafloor or stopped short as a blind intrusion is still not conclusively established. No eruption was detected above the site. But the absence of a detected eruption does not prove that no eruption occurred. Eruptions at slow W-spreading ridges produce much less lava than those at fast-spreading ridges, and small eruptions may not produce the hydrothermal plumes that the most reliable eruption detection methods rely on. The core problem is one of physics as much as technology. Magma, in the oceanic crust, moves in ways that are similar in principle to magma in continental settings, but different in detail. The oceanic crust is thinner, colder at depth than continental crust, and under different stress conditions. The magma reservoir geometry at slow-spreading ridges like the Mid-Atlantic Ridge is less clear than at fast-spreading ridges, where melt lenses near the ridge axis are well documented seismically. At slow-spreading ridges, magma supply is more episodic and less continuous, making the system less predictable. The 2026 Frontiers paper's systematic analysis of 24 years of swarm data addresses one part of this problem, establishing the statistical baseline for swarm behavior on the northern Mid-Atlantic Ridge. Without knowing what swarms look like when they are pu-reli tectonic and what they look like when they are magmatically driven, it is impossible to identify which category any particular swarm belongs to. The paper's contribution is to begin building that baseline using the longest available dataset. While acknowledging that the global catalog alone may not be sufficient for reliable classification without local instrumentation. Beyond the specific question of eruption prediction, the Mid-Atlantic Ridge has been at the center of a broader reassessment of what drives plate tectonics. The standard model of plate tectonics, as taught in most textbooks, presents the forces driving plate motion in a hierarchy. Slab pull, the gravitational drag of the dense, cold, subducting oceanic crust sinking into the mantle, is the primary driver. Ridge E, push, the force created by the elevated topography of mid-ocean ridges, and the gravitational spreading of the hot new crust, is a secondary contribution. And basal drag, The viscous coupling between the moving plates and the underlying mantle can act as either a driver or a resistance depending on the geometry. The Southampton 2021 Nature study challenged this picture at the level of the ridge itself. Their mantle imaging beneath the equatorial mid-Atlantic ridge showed a thin, hot mantle transition zone that they interpret as evidence of active upwelling from dPTH, an ascending current of hot mantle material that is pushing material toward the surface, rather than simply allowing it to rise passively into the space created by the parting plates. This distinction, active upwelling versus passive filling, has large implications. If the ridge is an active upwelling system, it is a driver of plate motion as much as a consequence of it. The force balance of plate tectonics in the Atlantic would need to be revised to account for an upward push from below, in addition to the pull from subducting slabs at the edges of the Pacific. The study's finding that the 1660 km seismic discontinuity is uplifted by about 10 kilometers over a swath roughly 600 kilometers wide implies material transfer from the lower to the upper mantle linked to the mid-Atlantic ridge, what the authors call evidence suggesting whole mantle convection may be more prevalent than previously thought, with ridge upwellings having a role in counterbalancing slab downwellings. The study acknowledges that this finding applies specifically to the equatorial ridge and may not be representative of the entire system, but it raises the question of whether active upwelling contributes to ridge dynamics elsewhere, and whether the documented deceleration in global seafloor spreading rates over the past 19 million years might be related to changes in the vigor of this upwelling, rather than purely to changes in slab dynamics at subduction zones. These are live questions with active research. The answers will come from more ocean bottom seismometer deployments, from improved mantle imaging, and from the continued analysis of swarm catalogs like the one developed in the 2026 Frontiers paper. There are three ways to frame what the mid-Atlantic ridge's activity represents, from the most immediate to the most geological. The first framing is the most immediate, an ongoing geological process producing real, measurable events in the present. The June 17, 2026 M6.6 earthquake is today's version of a process that produced the first Atlantic seafloor 180 million years ago. The 2022 seismic sequence at 54 degrees N was a dike intrusion event, magma entering the crust, potentially adding new material to the oceanic crust. These events are not geological curiosities from a textbook. They are happening now, this year, with instruments recording them in real time. The second framing is the longer geological one. The mid-Atlantic ridge as the machine that made the Atlantic Ocean. 180 million years ago, the Atlantic was a rift, a continental crack comparable in size to the current East African rift system. Over the subsequent 180 million years, that rift grew into an ocean 6,000 kilometers wide, through the accumulation of millions of individual dike intrusions and lava flows, each adding a few millimeters to the separation between the plates. What the monitoring system now records in real time, the individual seismic swarms and dike events, is the individual heartbeat of a process whose cumulative effect is the Atlantic Ocean. The third framing is the most fundamental. The mid-Atlantic ridge as a window into how the interior of the Earth works. The mantle beneath the ridge is being probed by earthquake imaging and by ocean bottom seismometers in ways that were not possible even 10 years ago. The 2021 Southampton study, using 39 instruments deployed for a year, produced a mantle cross-section beneath a portion of the equatorial ridge that challenges how the ridge dynamics have been modeled. More deployments, in more places, will produce more cross-sections, and eventually a three-dimensional picture of the mantle beneath the Atlantic that no previous instrument could provide. The crack in the Atlantic floor is not just a crack. It is a seam that, millimeter by millimeter, year by year, swarm by swarm, is remaking the planet. There is one more comparison that illuminates the Mid-Atlantic Ridge story, even though it involves a completely different location. The East African Rift System is the Atlantic Ocean in its infancy, where the Mid-Atlantic Ridge is a mature ocean basin, spreading quietly beneath 2,000 to 3,000 meters of water. The East African Rift is a continent in the early stages of being pulled apart, still above sea level, accessible to direct observation, and actively producing the same class of geological events that the Mid-Atlantic Ridge produces in the dark. In September 2005, a 60-kilometer crack opened in the Afar Desert in northern Ethiopia in a matter of days. A dike intruded into the continental crust, the surface fractured, and what geologists believe is the earliest stage of a new ocean basin announced itself in a way that no submarine event could have. Subsequent activity in the Afar region has continued, with periodic dike intrusions and fissure eruptions occurring at intervals of years, each one adding to the cumulative opening of the rift. The East African Rift has something the Mid-Atlantic Ridge does not: accessibility. GPS networks deployed across the rift can measure the surface deformation that accompanies dike intrusions directly. Seismic networks, with stations only tens of kilometers from active rift segments, can record earthquakes with the kind of precision and spatial resolution that the Mid-Atlantic Ridge will only receive when ocean-bottom seismometers are deployed nearby. Aerial and satellite observation can directly image surface features created by eruptions and intrusions. This is why the East African Rift has become such a valuable laboratory for understanding processes that, beneath the Atlantic, must be inferred from the seismic signals and acoustic waves that make it through the water column to distant instruments. What geologists learn from the Afar Rift about how dikes propagate, how the surface responds to intrusion, and what seismic signatures accompany specific stages of the intrusion process, can be applied to interpret the more ambiguous signals from the submarine ridge. The two systems are not identical. Continental rifting and oceanic spreading differ in important ways, but the family resemblance is close enough that insights from one illuminate the other. That is a story for another time. Let's come back to where we started. A magnitude 6.6 earthquake on the central Mid-Atlantic Ridge, June 17, 2026. 168 seismic stations recording its passage through the planet. No damage, no threat to any coastline, no tsunami. A geological event that most people on Earth will never hear about. And yet, this earthquake is a moment in the process by which the Atlantic Ocean grows. A moment in a process that has been running continuously for 180 million years. A process that the 2022 sequence at 54 degrees N let scientists watch in detail as a dike propagated southward through the oceanic crust at 0.6 kilometers per hour over several weeks. A process that the 2021 Southampton Nature paper revealed may be driven not just by passive plate separation, but by active upwelling from the deep mantle. A process a February 2026 paper is working to characterize systematically, using 24 years of earthquake data from the northern ridge. The crack has been growing for 180 million years. It is growing today. It will be growing tomorrow. What has changed in the past few years is how clearly we can see it happening. A generation ago, the 2022 event at 54 degrees N would have been detectable as a significant seismic sequence. but the southward migration of the dike tip at 0.6 km/h would not have been resolvable from the available data, in the way that Seska and colleagues' analysis achieved. A generation ago, the mantle structure beneath the equatorial mid-Atlantic ridge was imaged only through global tomography models with limited resolution. The detailed receiver function analysis that revealed the thin transition zone required the local ocean bottom seismometers of the PILAB experiment. A generation ago, a systematic 24-year analysis of swarm catalogs along a 100-kilometer stretch of ridge was not computationally practical with the methods then available. The geology has not changed. What has changed is the resolution with which we can observe it. The mid-ocean ridge system is one of the most consequential geological features on Earth. It produces 2/3 of all new oceanic crust generated globally. It hosts the largest hydrothermal vent ecosystem in the ocean. It is the mechanism by which the Earth's interior heat is transported to the seafloor, and from there to the ocean above. And it is the site of continuous geological activity, seismic swarms, dike intrusions, eruptions, and hydrothermal events, that collectively constitute one of the most active geological environments on the planet. It receives a fraction of the public and media attention given to continental volcanic systems, earthquake zones, and geological hazards that threaten human populations. Here are the specific aspects of the mid-Atlantic ridge story that most coverage misses or misrepresents. The first is what seafloor spreading actually looks like at the scale of individual events. Popular accounts of plate tectonics describe the process at the scale of millions of years, continents drifting, oceans opening and closing. The 2022 event at 54 degrees N showed what seafloor spreading looks like at the scale of days. A dike propagating through the crust, earthquakes migrating southward, ridge flanks being pushed into compression as the central intrusion inflates. This scale of observation, individual geological events producing the slow cumulative change, is essentially absent from popular accounts of plate tectonics. The second is the 2021 Southampton Nature finding. The result that the equatorial mid-Atlantic ridge has evidence of active upwelling from the mantle transition zone, challenging the passive ridge model that has been standard in textbooks, received reasonable scientific coverage when the paper was published in January 2021. It has not been incorporated into the popular understanding of how mid-ocean ridges work. The story that ridges might be actively driven from below rather than passively filled from above remains largely confined to the specialist literature. Popular coverage often dates this finding incorrectly to 2022, confusing it with the GRL paper on the 54 degrees N seismic sequence. The third is the prediction problem. The question of whether a seismic swarm on the mid-Atlantic ridge is going to produce a submarine volcanic eruption is not a solved problem. It is an active research question with important implications for understanding hydrothermal vent ecosystems, which are among the most unusual and scientifically important biological communities on Earth. Most popular science coverage treats seafloor spreading as a well-understood background process, rather than a frontier of active research with genuine open questions. The fourth is the monitoring gap. The mid-Atlantic ridge is 16,000 kilometers long. The coverage by ocean bottom seismometers at any given time is a tiny fraction of this length. The global seismic network, while comprehensive for large events, cannot provide the resolution needed to distinguish magmatic from tectonic swarms along most of the ridge. This monitoring gap is a real limitation on what we know and when we know it, and it explains why events like the 2022 sequence can only be fully understood retrospectively rather than in real time. The fifth is the connection between ridge activity and deep ocean biology. Hydrothermal vent communities, supported by chemosynthetic bacteria that derive energy from chemical reactions between vent fluids and seawater, rather than from sunlight, are extraordinary ecosystems of scientific importance for understanding how life can exist without solar energy. Submarine volcanic eruptions at mid-ocean ridges can wipe out established vent communities and create new ones. The ability to predict such eruptions would transform the study of these ecosystems. That connection between the geophysics of ridge spreading and the biology of the deep ocean is almost never made in popular accounts of either topic. The two most recent significant developments for understanding mid-Atlantic ridge activity are the February 2026 Frontiers in Earth Science paper and the June 2026 M6.6 earthquake. The Zhang, Rich, and Heron 2026 paper focused on a specific stretch of the northern mid-Atlantic ridge between 52 and 63 degrees north, a portion that includes the Reykjanes Ridge extending south from Iceland. This stretch has a longer and more detailed observational history than most of the ridge, partly because of its relative proximity to land-based monitoring stations in Iceland, the UK, and North America, and partly because it has been the subject of focused scientific interest due to its position at the junction between the Mid-Atlantic Ridge System and the Iceland hotspot, where elevated mantle temperatures produce unusual volcanic and geological activity. The paper analyzed ISG's earthquake catalog data from 2000 through September 2024, identifying swarm events using cluster analysis algorithms. The team developed a Python module specifically for this analysis, also published as a separate Frontiers contribution, that systematically identifies swarms from global earthquake catalogs based on spatial and temporal clustering parameters. This tool is publicly available, meaning other researchers can apply the same methodology to other ridge segments or time per iods, potentially building a comparable systematic picture for the full length of the Mid-Atlantic Ridge or for other mid-ocean ridge systems globally. The analysis characterized swarms by their duration, the number of earthquakes they contain, their spatial extent along the ridge axis, and whether they show any systematic migration of seismicity. The result is a statistical picture of swarm behavior in his portion of the ridge over 24 years, which swarms are common and brief, which are long and involve many earthquakes, and which show evidence of spatial migration that might indicate a migrating dike. The honest conclusion about what this analysis can and cannot do is instructive. The global catalog is sufficient to detect swarms and characterize their gross properties. But the location uncertainties, typically several kilometers for events on the Mid-Atlantic Ridge using land-based monitoring, and the magnitude detection threshold, typically around M2.5 to M3 for the ridge, are large enough that the most diagnostic features of a magmatic swarm are often not resolvable. The precise migration rate, Tha-T, was the key diagnostic for the 2022 54 degrees N event, for example, would be very difficult to establish reliably from global catalog data for a smaller event or one where the migration rate was slower. This conclusion has a practical implication. Systematic swarm characterization for the full length of the Mid-Atlantic Ridge, of the kind needed to understand the statistical relationship between swarm properties and subsequent eruptions or dike intrusions, will require denser monitoring than global networks can provide. The 2026 paper is an important step toward that goal, establishing what can be learned from global data alone, but it also clearly delineates where that approach reaches its limits. The June 2026 M6.6 earthquake represents the ongoing background against which this research is being conducted. It occurred on the central mid-Atlantic ridge, in a region with less systematic swarm analysis than the northern portion covered by the 2026 PAP-ER. Whether it was associated with a dike intrusion, whether a swarm preceded or followed it, and what its focal mechanism reveals about the local stress state of the ridge. These are questions that will be analyzed in the weeks and months following the event, using the tools and methods described above. The research agenda for mid-Atlantic ridge science over the next decade is shaped by the specific gaps identified in recent work. The most immediate need is expanded ocean bottom seismometer coverage. The cost and logistical challenge of deploying ocean bottom seismometers at scale is significant. Instruments are expensive, deployments require research vessels, and data recovery requires returning to specific seafloor locations a year or more after the initial deployment. But the scientific return is high. Local seismometer coverage turns ambiguous swarms in the global catalog into detailed studies of crack propagation, magma migration, and crustal stress, the kind of data that actually constrains the physics of seafloor spreading. The 2021 Southampton study showed what 39 instruments deployed for 1 year can reveal about mantle structure that was invisible to global monitoring. Scaling that approach to cover more of the ridge's length, more systematically, would transform what is currently an episodic and incomplete picture into something approaching comprehensive monitoring. New, autonomous underwater vehicle technology is beginning to provide additional monitoring options. Gliders and AUVs capable of sustained ocean floor surveys can detect changes in water chemistry, temperature, and turbidity above active spreading segments, providing indirect evidence of hydrothermal activity that may accompany eruptions. These platforms are not as sensitive as fixed ocean bottom seismometers, but they can cover much larger areas, providing a wider but shallower view of ridge activity. An eruption that goes undetected because no ocean bottom seismometer is in the area might still be detected by an AUV monitoring water column properties above the ridge, a less precise signal but a broader coverage. The specific question of active upwelling raised by the 2021 Southampton Nature paper needs follow-up deployments at other portions of the ridge. The equatorial ridge, where the PILAB experiment was conducted, has specific geological history. It sits near a major fracture zone system and has a particular pattern of ridge segmentation. Whether the thin mantle transition zone found there is unique to this location or representative of the broader ridge system is unknown. Future experiments designed to image Tehe mantle beneath the northern or southern mid-Atlantic ridge, using similar ocean bottom seismometer techniques, would either confirm or bound the upwelling interpretation. If upwelling is found beneath other ridge segments as well, the active mantle contribution to spreading is probably a general feature of the system. If it is confined to the equatorial section, the implication is that this particular segment has a different driving mechanism than the rest, and the link between seismic swarm properties and subsequent eruptions, the prediction problem, will be advanced as more events are observed with local instruments. Each well-documented dike intrusion event adds to the catalog of what a spreading event looks like seismically, making the discrimination between magmatic and tectonic swarms slightly more reliable for subsequent events. The 2022-54 degrees N event, analyzed retrospectively, adds one detailed case study. If a similarly instrumented region experiences another dike event, the comparison will be more constrained. The slow accumulation of well-documented events, each contributing to the statistical picture of what magmatic swarms look like, is how the prediction problem will eventually be resolved. The answer to whether mid-Atlantic ridge eruptions can be predicted is not yes today. Whether it will be yes in 20 years depends on decisions being made now about monitoring investment. Here is what the Mid-Atlantic Ridge, watched carefully over the past several years, actually reveals. The Earth is not a finished planet. The distribution of continents and oceans that we take as the backdrop of human geography, the map that humans have been drawing for 5 centuries, is a transient configuration. The Atlantic Ocean is younger than the dinosaurs. The mid-Atlantic ridge that is creating it is not maintaining a static ocean, but growing one. North America and Europe are 5 centimeters further apart today than they were a year ago. They will be 5 centimeters further apart a year from now. Most of this growth happens silently, millimeter by millimeter, in individual dike intrusions that produce small earthquakes detected only by instruments and analyzed only by specialists. Occasionally, a dike intrusion is large enough, and the resulting seismic sequence dramatic enough, to produce detailed data like the 2022 sequence at 54 degrees N, giving scientists a brief, clear view of the process in action at the individual event scale. And, occasionally, a magnitude 6 earthquake occurs, large enough to be recorded by 168 stations around the world, a single moment in a process so continuous and so ancient that it is easy to think of as background geology rather than present geology. But it is present geology. The Mid-Atlantic Ridge is not ancient history preserved in rock. It is an ongoing event. The June 2026 earthquake is not a record of something that happened in the geological past. It is something that happened last week, in a process that has been running without pause since before the dinosaurs appeared, and that will continue running long after any human institution that currently monitors it has ceased to exist. There is a perspective that is difficult to hold but worth attempting. In the year that this video was made, the Atlantic Ocean is approximately 500 kilometers wide at the latitude of the equatorial ridge. In 50 million years, if spreading continues at its current rate, it will be approximately 750 kilometers wide. In 100 million years, it will be approximately 7,000 kilometers wide. The continents that ring the Atlantic today will have moved to positions that would be unrecognizable on any current map. South America, Africa, Europe, and North America will be further from each other than they are now, or they may have begun to converge toward each other as new subduction zones form along the Atlantic margins. The current models of long-term plate motion disagree about which future the Atlantic faces. What is not in question is that the process producing the Atlantic's current configuration has not stopped. The crack is still growing. Every year, the evidence accumulates in the seismic catalogs of the USGS and other networks, and in the rare, detailed observations like the 2022 54 degrees N sequence that give scientists a close-up view of the mechanism. The crack in the Atlantic Ocean floor is not a new crack and not a remarkable crack. It is just the crack, the one that has been there for 180 million years, doing what it has always done, measured now by sensors that barely existed a generation ago, and understood now in a way that was not possible before the ocean bottom seismometers of the Southampton PILAB deployment gave scientists their clearest direct view of what happens beneath the ridge. The crack is growing. It has been growing for years. It will be growing tomorrow, and next year, and for the next 100 million years. What we are just now learning to do is watch it grow in something close to real time. There is one more thread connected to this story. The Mid-Atlantic Ridge is the most extensive active geological feature on Earth. But there is another class of spreading system, separate from the mid-ocean ridge network, that is producing the most spectacular evidence of how continents are torn apart in real time. The East African Rift System, stretching from the Afar Triangle in Ethiopia and Eritrea south through Kenya, Tanzania, and Mozambique, is in the earliest stages of the process that created the Atlantic. In 2005, a 60-kilometer crack opened in the Afar Desert in a matter of days, as a dike intruded and the surface ruptured. Subsequent activity in the Afar region has continued a pattern of intermittent rifting that geologists believe will, over millions of years, allow the sea to flood in and create a new ocean. The East African Rift is the Atlantic Ocean in its infancy. And because it is above water, on land, accessible to GPS networks and direct observation, it is the best natural laboratory for understanding the process that, beneath the Atlantic, we can only monitor from afar. That is a story for another time. We started with a magnitude 6.6 earthquake on the central Mid-Atlantic Ridge, June 17, 2026. An event recorded by 168 seismic stations. No tsunami, no casualties, no damage, and yet a moment in the ongoing process by which the Atlantic Ocean grows. Then we traced that process to its details. The 2022 sequence at 54 degrees N, where more than 60 earthquakes over several weeks traced the southward migration of a dike through the oceanic crust at roughly 0.6 kilometers per hour, with compressional aftershocks 25 kilometers on each side, as the intruding magma squeezed the ridge flanks outward, pushing the ridge into an unexpected mode of failure in a region where compression should not occur. A physical picture of what individual spreading events look like, at T scale of days and kilometers. The 2021 Southampton Nature Study, where 39 ocean-bottom seismometers deployed for a year, revealed a thin, hot mantle transition zone beneath the equatorial ridge, evidence of active upwelling from the deep mantle that challenges the passive ridge model T-hat has been standard in textbooks since plate tectonics was established. A fundamental revision in how we understand what drives the system. The February 2026 Frontiers paper by Zhang, Rich, and Heron, 24 years of swarm data from the Northern Ridge, analyzed with cluster algorithms to build the first systematic statistical picture of swarm behavior in this region, a foundational effort to understand the baseline against which any individual event must be compared. And throughout, the monitoring gap, a 16,000-kilometer feature with significant geological activity, producing events whose interpretation requires local instruments that cover only a tiny fraction of the ridge at any given time. A monitoring system that is comprehensive for large events, but limited for the kind of detailed characterization needed to distinguish magmatic from tectonic swarms along most of the ridge's length. The crack in the Atlantic floor is old, the monitoring is new. The understanding is in progress. Each decade, the picture gets somewhat clearer, more swarm events documented, more mantle structure imaged, more detailed physical models of dike propagation. The June 2026 M6.6 earthquake is one more data point in this ongoing effort to understand a geological process that has been reshaping the planet for 180 million years. Whether the June 2026 M6.6 earthquake was associated with a dike intrusion or was a purely tectonic event has not yet been determined as of this recording. focal mechanism analysis will establish whether the earthquake ruptured in extension, normal fault in G, typical for the ridge axis, or in a different mode. Aftershock distribution studies will establish whether the events cluster along a linear trend that might indicate a propagating dike tip. These analyses will take weeks to months following the event, using global network data, or could be done more rapidly if any ocean bottom seismometers happen to be deployed in the region at the time of the earthquake, which, given the monitoring gap, is unlikely. Whether the active upwelling identified beneath the equatorial mid-Atlantic ridge by the 2021 Southampton study is present elsewhere along the ridge, and what its contribution to the overall driving force of spreading is, remains an open research question. The mantle beneath other portions of the ridge, the Reykjanes Ridge near Iceland, the South Atlantic Ridge near the mid-latitude portions, has not been imaged with the same receiver function technique using local ocean bottom seismometers. Future experiments, designed to replicate the PILAB approach at different latitudes, would either confirm the upwelling as a global feature of the ridge or show that it is specific to the equatorial segment. Whether any particular seismic swarm on the mid-Atlantic ridge can be predicted to produce a submarine volcanic eruption is not currently possible with available monitoring. The 2022 54 degrees N event, the best documented recent dike intrusion on the ridge, was ONLY fully interpreted retrospectively, real-time detection of a migrating dike tip, which would be the prerequisite for any kind of eruption warning, requires local instrumentation that is not currently available for most of the ridge. The detailed structure of the magmatic system beneath the slow-spreading mid-Atlantic ridge, specifically the question of whether continuous melt lenses near the axis feed the spreading system, or whether magma ascends episodically from depth without forming sustained reservoirs, is less well resolved than the analogous question for fast-spreading ridges, where seismic surveys have directly imaged melt lenses. The answer affects how the ridge responds to changes in magma supply over time, and how predictably the eruption pattern is likely to be. And the global deceleration in seafloor spreading rates, documented in other studies, with some evidence that global average spreading rates have decreased by tens of % over the past tens of millions of years, whose cause is not fully understood. Remains a significant open question for the long-term dynamics of the plate tectonic system. If the upwelling discovered at the equatorial ridge is a general feature, changes in the vigor of that upwelling over geological time might contribute to the observed spreading deceleration, a connection that would link the local process observed in the 2021 Southampton study to the global behavior of the plate tectonic system. First, the most consequential geological processes are often the least visible. The mid-Atlantic ridge produces no eruptions visible at the surface, no tsunamis, no volcanic ash clouds. It produces a continuous background of seismic activity, detected by eye instruments but felt by no human being, while slowly growing the Atlantic Ocean one dike intrusion at a time. This invisibility is not accidental. It is the direct result of the geometry of a submarine rift valley at depth of 2,000 to 3,000 meters. The MOS-T consequential seafloor geology on Earth happens beneath a layer of ocean that puts it entirely out of reach of direct human experience. And this goes a long way toward explaining why it receives so little public attention relative to its importance. Second, the scale mismatch between individual events and geological outcomes is a fundamental feature of Earth science. The 2022 dike intrusion at 54 degrees N added, at most, a relatively thin layer of new crustal material to the ridge over a few weeks. A single dike intrusion event contributes perhaps a meter or two of new crust to a ridge that has accumulated kilometers of oceanic crust over millions of years. Understanding how individual events sum to large-scale change over long timescales is one of the central problems of geology, and it requires precisely the kind of systematic swarm analysis that the 2026 Frontiers paper is attempting, building a statistical picture of many events, rather than focusing only on spectacular individual ones. Third, the passive ridge model that dominated geological thinking for most of the 20th century is now actively contested by evidence of deep mantle upwelling beneath at least portions of the ridge. The 2021 Southampton Nature paper is the clearest expression of this challenge. What was thought to be a passive consequence of plate separation may have active mantle dynamics contributing to it. The standard textbook account of plate tectonics may need revision at the level of what drives mid-ocean ridge activity. This is not a small revision. If upwelling from the lower mantle contributes significantly to ridge spreading, the force balance of the global plate tectonic system needs to be reconsidered, and the conventional hierarchy of slab pull, ridge push, and basal drag as the primary drivers of plate motion is incomplete. Fourth, monitoring determines understanding. The 2022 sequence at 54 degrees N was understood in as much detail as it was because global seismic networks detected it, and researchers had the analytical tools to interpret the migration pattern. With local ocean bottom seismometers, the interpretation would have been more precise, the migration rate better constrained, the extent of the dike more clearly mapped, the presence or absence of any eruption more definitively established. Without the global network, the event would have been invisible. What we know about the mid-Atlantic ridge is a direct function of what we have measured it with. This is true more broadly. Scientific knowledge of any system is bounded by the instruments available to measure it, and the monitoring gap for the mid-Atlantic ridge represents a real limit on what we currently know about one of the most active geological systems on Earth. Fifth, the Atlantic Ocean is not a fixed feature of the Earth's surface. It is an ongoing process, currently producing several centimeters of new seafloor per year along its entire length, and has been doing so continuously for 180 million years. The map of the Atlantic that humans have drawn for 5 centuries is a snapshot of a transient configuration, one frame in a geological film that will look very different in another 180 million years. And that looked dramatically different 180 million years ago. The landmasses now separated by the Atlantic were joined together. Recognizing this, that the geography we take as given is itself a momentary outcome of a process that has been running for far longer than our species has existed, is one of the deepest conceptual shifts that understanding plate tectonics can produce. The Atlantic Ocean is 180 million years old and is still growing. Human civilization is roughly 12,000 years old. What does it mean to think about geological processes that began before our species existed and will continue long after it is gone? And to recognize that the landscape we inhabit is a temporary configuration in an ongoing process. The Atlantic will look different in 50 million years than it does today. The continents are in a different configuration now than they were when our genus first appeared, and will be in a different configuration again when, if we are still around to notice, the next geological epoch makes itself felt in the shape of the land. The mid-Atlantic ridge is the most important geological feature in the Atlantic, and it receives a fraction of the public attention given to land-based volcanoes and earthquakes that affect human populations. Is this an appropriate prioritization of scientific communication? Or does the invisibility of the ridge reflect a systematic bias in how geological importance is communicated? There is an argument to be made that the geological processes happening beneath the Atlantic deserve as much public attention as the ones happening beneath Iceland or Hawaii, or the Pacific Ring of Fire. They are just as consequential for how the planet is shaped over geological time, simply invisible because they happen to occur beneath a body of water rather than beneath land. And more practically, the global seismic network can detect a M6 earthquake on the mid-Atlantic ridge within minutes of its occurrence, but cannot tell you whether that earthquake is associated with magma entering the crust. What would it take to close T-hat monitoring gap, and who should pay for it? The ocean covers 71% of Earth's surface, and the most geologically active portion of that surface, the mid-ocean ridge system, is among the least monitored. The instrumentation gap is not a technical problem. The technology exists: ocean bottom seismometers, hydrophone arrays, AUV surveys. It is a question of scientific priorities and international coordination. A globally coordinated program to install permanent or semi-permanent monitoring on key segments of the mid-ocean ridge system, modeled on the land seismic networks that allow comprehensive monitoring of continental earthquake zones, would transform what is currently a fragmentary picture into a comprehensive one. The cost would be significant. The return, in terms of understanding the most active geological boundary on Earth, would be enormous. There is one more dimension to the Mid-Atlantic Ridge story that deserves brief mention, because it connects the geology to some of the most extraordinary biology on Earth. Hydrothermal vents are seafloor features associated with mid-ocean ridges where seawater percolates down through cracks in the oceanic crust, is heated by contact with hot rock near the magma system, and returns to the seafloor carrying dissolved minerals. These vent systems support communities of organisms unlike any found anywhere else on Earth: tube worms, vent shrimp, chemosynthetic bacteria, that derive their energy not from sunlight but from the chemical energy in the hydrothermal fluids. They exist because the ridge is geologically active. Every dike intrusion, every spreading event, every pulse of new magma into the crust potentially affects the hydrothermal systems that support these communities. Submarine, volcanic eruptions can destroy existing vent fields by burying them under new lava. But they also create new vent fields, as the heat from fresh lava drives new hydrothermal circulation through cracks in the newly formed crust. The biology of hydrothermal vent communities is inseparable from the geology of the ridge that hosts them. Predicting eruptions, the monitoring problem discussed throughout this video, would not just advance geological understanding. It would enable biologists to observe Tihee effects of eruptions on vent communities in real time, rather than arriving to find a community already destroyed or a new one already established. The monitoring problem has biological stakes as well as geological ones. This is another dimension of the Mid-Atlantic Ridge story that receives almost no attention in popular accounts of either the geology or the biology. The hidden crack growing in the Atlantic floor is not just reshaping the planet's geography. It is, moment by moment, determining the conditions for life in the deep ocean in ways that we are only beginning to understand. If this one stayed with you, let us know which part landed hardest. The June 2026 M6 and what it represents. The 2022 dike event at 54 degrees N, earthquakes over weeks tracing magma through the crust at 0.6 km/h. The 2021 Southampton discovery of active upwell ling beneath the equatorial ridge, challenging the passive model. The monitoring gap, a 16,000 kilometer active geological system with local instrumentation covering a fraction of a percent of its length. Or, the closing realization that the Atlantic Ocean is not a geographical fact, but an ongoing geological event. 2, 5 centimeters larger today than it was a year ago, and growing. And, if you want more of this, real Earth science at the scale where individual events become geological history, subscribe to Galaxy Pulse, and we will see you in the next one. Somewhere in the central Atlantic Ocean, the seafloor is cracking open. It has been cracking open for 180 million years. A magnitude 6.6 earthquake marked the latest moment. 168 instruments recorded it. The rock moved a few centimeters, new crust formed, or will form, in the gap. The Atlantic grew, fractionally, one more time. Tomorrow it will grow again, and the day after, and on every day for as long as the ridge remains. We are only just learning to watch it happen.